The title and content of this talk have kind of evolved since I first wrote the abstract for the Build Stuff site, but I checked it last night and it's still roughly on par. It's now called Zero Support Production. I think it's catchier. It's good. So I'm Rob Ashton. I used to do quite a lot of talk about JavaScript and stuff, and then the last 2 or 3 years I've kind of just bolted myself in a room and worked at this company, Ideas. And Ideas, the company I work for, fine. What we build is bespoke media workflows, which is a fancy way of saying we do like on-demand video encoding and delivery to like CDNs and such like that. But these are systems that are designed for the customers. We don't have a product in a box, everything we build is for them. Like, classic example is something like that. Nice complicated architecture diagrams, lots of moving parts, lots of failover, lots of inputs, lots of outputs, great stuff. But the kind of thing we do is obviously like on-demand encoding, delivery. We do live web-based editing of video. So when there's these 24-hour-long events that one of our clients runs, they can edit as the event's running and cut all the toilet breaks out of it so they don't get pushed into the final version. We do things like remote commentary, so like sports events. They can now do remote working, they can sit at home, use WebRTC and commentate on live sports events. And we'll do things like match the timestamps so the output's correct. So when they're saying things on stream and seeing things, that matches the output. And it's like they're actually live, which is nice. Obviously we take external audio feeds as well. Lots of combinations of all of these, and every customer is indeed a special snowflake, which is why we do this in the first place. Most of the time we are building these systems because they've tried to do it internally and failed, because having a team of hundreds of developers tends to make you unable to actually deliver anything. And with this stack, we're currently doing hundreds of thousands of live events every year, as well as quite a lot of static channels. And we don't get any support in production. We're doing that. So we have 4 people in the entire programming team. That's them. My friend Steers is me, it's Steve Major, big guys. And we build everything ourselves in-house, and we are now having 7 or 8 really big clients doing these big complicated systems. We have a good support team, one ops team, the same 4 people, and indeed our support team are the same 4 people as well. I actually cropped a guy out of this because he doesn't do any work. His job is to go and get business. He goes to conferences and smooches for people, and everyone likes him. So they have a little confab together, and eventually they come and talk to that guy there who makes them agree to give us lots of money to build these things, and then we go off and surprise them by doing things in like 2 weeks when they can't do things in 2 years. Classic example is remote commentary. One our customer had previously tried to build it for 3 years, which didn't get anywhere, and we built it in 2 weeks and just gave it to them when asked what he wanted to write, and like mind blown, it's good stuff. So not only are we having to build quite a lot of new stuff for our clients, we have to support all these systems, as I said, we have support contracts. We don't want to spend time supporting the old stuff. We want to get paid money to support it, but we don't actually want to support it. There's a big thing there, isn't there? I mean, every day I'm sat crawling through logs and production system. It is a day I'm not spending building new stuff, which we also get paid for. And we get paid a lot more money to build new stuff than we do to support old stuff. Support contracts are lucrative, but you don't want to actually incur the cost of doing that. So a good example of one of our customers, again, I'm trying not to mention names of customers in this talk because I tend to run my mouth off quite a lot, so I don't want to say something that they would get upset with. One of our customers does all the Freeview TV in the UK, so and stuff, digital TV, and they've not called us for a support instance in any environment, never mind live, in 3.5 years. It just sits there running and doing its stuff, and it's happy. Every now and then we go in and have a conversation with them about anything they might want to see in the future. But they're just paying money per channel and getting on with it, which is nice. That's the ideal situation, really. That's where I want to be. So the way I'm going to go through this entire talk is I'm just going to talk about our approach to doing things all over the stack. It's not a terribly cohesive talk, but it's accumulation of our experience over the last, I'll say, half-decade, really, of building these kinds of systems and how we do that. So hopefully there's some useful stuff in there. This is not an Erlang talk. There's some Erlang in it, but it's not an Erlang talk. So God help me, I think I've been asked to run functional tracks into this talk so many times this year. I can't do it because it's not a functional programming talk. So let's start with code. Let's get it out of the way and done with. No one actually really likes code all that much, but we'll talk about it. So we write all of our code assuming it's going to get thrown away, at least to begin with anyway. We write code in a way that every single file is something you can delete fairly easily and recreate if needed to, doing something different. We do that because if you can do that, you can react to change very quickly. We also reuse absolutely everything we can. So again, we're a team of 4 people. We don't want to be reinventing the wheel every single time we build a new system, so we have lots of very big core libraries for doing all the basic heavy lifting with video, all the basic heavy lifting with orchestration and scheduling and auctioning across the cloud, all that other stuff's all reused. And everything ends up going in a Dropbox. We don't use third-party code as much as we can, except when we do, because there are some things out there which we shouldn't do ourselves. A good example of that would be our HTTP server. We use Cowboy from Loic. Great, you know, it does its job. You set up resources and you can build endpoints to talk to. Brilliant stuff. We're not going to go and build a HTTP stack, that would be crazy. But for anything that's core business, for example, any protocol that we consume or spit out, we might look at other people's work if it's out there, but generally we'll either bring in that code, own it, or we'll write our own. So things like WebRTC, we've got our own stack for that, we built that. SIP, got our own stack for that, we do that. Even our way of talking database, etcd, we've written our own thing for that. It's important. So we have to own our third-party code. This is really important. Every time you bring in a dependency, any kind of programming environment, you are bringing in someone else's code. And I remember from my C# days, everyone had a dependency on the newtonsoft.json.dll, whatever it was called. And you get a bug in that, your approach to actually going to fix that is, well, again, back in the day, now you're up to GitHub and do things with it, was to go and find the source code for that, whether that was a living, I think it was SourceForge at the time. You had to bring that down to your computer, you had to find the bug, you had to fix it. Testing it meant removing the DLL from your project and kind of building a DLL and putting it over here and moving things around. And because of this effort and because of this lack of understanding that this was code that you brought in, people never actually submitted big fixes for that. Basically, whatever his name is, Newton, basically had to build everything himself all the time. No one had to. I was very done anything. Obviously, you've got package managers, you bring things in whenever you want to, but still, you still bring in code. So we actually order all code, we bring it in. Obviously, we don't use everything. Don't use everything. Use everything, but don't use everything. Very often, copying and pasting a file is not effective, for the most part. Whenever we have a client that does one thing slightly different to the client, if it is something that's really core, then that's great. We can just add some more config to it, change it around a little bit. But a lot of the time, if it's less than 500 lines of code, you just bring it into the project. And that's fine. They'll diverge over time, and they will diverge over time. And maybe once or 2 or 3 times, you might then go, I now know what packages are, I'll make a core library for that, and we'll delete all this piece of the code over here, and replace this thing over here. Important. When it comes to code quality, it's actually really important. We write all of our UIs in Elm and have done now for 3 years. You've all heard of Elm? You should be using it. If you're writing JavaScript, you're like in the Ansible like box together. Elm is absolutely brilliant. I don't think it's the right answer yet, but it's better out there, it's going to come. But having a very simple architecture almost enforced upon you, and having type safety and not being able to introduce runtime errors into your UIs generally makes sense. So everything's now done in this, which is very nice, it's good. This is a bit of Erlang. If you read that, it's a bit horrible colour actually, isn't it? So, Erlang, the first pass. Do you know Erlang? Anyone here actually know Erlang? Okay, that's good. Well, what we have here is a record called container with something called value inside the container. We've got a function that takes 2 containers, adds them together to this new container. That's great. There's no information in this. There's no type information. There's no tests. There's nothing to actually guide the quality of this code. A lot of our code, first pass, looks a bit like this. Second pass, you might add some tests because you kind of understand now what it's meant to be doing. We don't do TDD. So much of the work that we do tends to be not understood while we're doing it. Customers don't know what they want, we don't know what they want. So we'll tend to throw things at the wall until the customer goes, yeah, you know what, that's what I wanted, that's brilliant, yeah, okay, it's good. And then we'll go, great, we've built what you wanted. it's really bad and awful. We'll have some tests to sort of guide around that side of things. And eventually, once we start having libraries, once things become core, you add type annotations, you add documentation, you have tests there, and that becomes something that lives in the core system that everyone understands and is documented. And you have to do things that way, because this gives us the ability to stylize over the code base and actually check that we're not passing integers into strings and crap like that. Because you can do that in Erlang. It's not a type-safe language. So it's nice having the ability to move into that. I know I'm quite a big fan of Haskell. Do you know Haskell here? So I've written quite a lot of Haskell. And I always find that it's quite slow to build anything of any size. And when you're prototyping, it's not really the best environment to be in for that, because you put all upfront effort in and then just throw it away, you've wasted all upfront effort. So if you're writing code to throw away like what you do, there's no point in trying to make it pretty, because you're going to leave it tomorrow anyway. There's nothing for that. So there is the need all code gets thrown away at some point. We make our mission to throw code away. So there's not much point worrying about quality the first time around. Once code's lasted for 3 iterations or so, we go, right, okay, no, that's actually something we like and we're going to keep. So we'll now make it good. But most of the time, we don't bother with that. Now, that obviously means we have bugs. We'll talk about it later. Our approach to system design. So we build quite elaborate systems. They have to be. For example, in one of the projects I'm on, we probably have 7 or 8 different firmware types, all have to kind of talk to each other in various ways, streaming video one way, streaming audio the other way. They need to be configured to do that, it needs to be correct. Obviously, things are being changed by the user or the external system all the time, that needs to come through here too. There's a lot of capacity for errors to creep in, either scheduling, orchestration, or just state bugs in general. So we have to be quite ruthless about the design of our systems. So the very first thing, this is a very motivational speaking slide, isn't it? Identify our absolute truths. Yeah, so this is the absolute truth. Absolute truths are things that you don't know most of the time. They're normally external data the client owns and gives it to you somehow. Either we're polling an API they've given us, or they're typing in things through a management UI of some sort, or they're pushing things in by API calls themselves. But regardless of the way you see it, it is an API. Even if typing things in through UI, that's still an API. To them, it's their interface to the system. So when they say that these are the channels in the system, these are the events now running, these are the events not now running, these are the commentary sessions that need to be done right now, this is a video editing system that needs to spin up over here, that's the absolute truth. They've told us what needs to happen in the system. And we don't change or mutate any of that, we don't own it. They're saying, this is the truth. And we go, cool, that's the truth. And from that truth, we can rebuild all of our state from scratch. And that's really important. So we don't generally create state that's anything less than transients. We should be able to delete most of our stuff and have the system rebuild itself from what they've given us. Obviously, this is not applicable to all systems. It's applicable to all the systems we build, though, which is great. It's a nice way of working. Very often, my approach to doing a release is just to RMR the whole production database and spin everything up again and rebuild for the source truth again. Because it's much easier to do migrations. And no one notices, it's fine. Erlang has the ability to do hot loading and 0 downtime for releases, but the effort of doing that is actually more than just turning everything off and on for 2 minutes. So we just turn everything off and on for 2 minutes. I mean, if you don't need it, don't use it, you know? So examples of this, like you guys say, channels, you've got input addresses, you've got output addresses, you've got all the codes needed for the channel, they give us all the information, we can't modify that. Anything transit like events, they get again given that to us, we don't modify that information. So from this config, we're able to identify jobs that need to run in the system, and when we run those jobs, and we can generate all these jobs from that absolute truth. Jobs to us are anything like self-contained, single-purpose. They're single units of failure. If one of them goes away, nothing else goes away. They just crash. That's fine. They've gone away. Never mind. They should be blind and autonomous. If the controller goes away, then they should carry on running. It's generally the principle of these systems. I think Stack did a Nomad talk yesterday. He's talking a little bit about how they managed that with Nomad. What I'm about to show you here is how effectively we built our own orchestration and scheduling system. We'll talk about that at the end as well. So anyway, you've got absolute source of truth at the top there. That's going to get given to some kind of controller, and that's going to generate some kind of job. So you see all the arrows are pointing that way. That's important because you're always pushing the data downstream. You're not having things pull data, you're not having things modify data, you're not having jobs talk to each other directly because it's just generally a bad idea. They are self-contained. So what that means is if a job goes away, everything else carries on running, it's absolutely fine. And if the controller goes away, well, the job's carry on being fine. That's not a problem at all. So that means ideally you should be able to like pull bits out of the system or turn things off, and the client doesn't notice anything happening downstream, for the most part. This is important. So data flow-wise, everything is entirely one way. So the controller receives the absolute truth and goes, great, I've got the absolute truth. This is the state of the world, and it has to look like this. So the controller can then assess the current situation. It's really S, isn't it? Assess, whatever. The controller can generate jobs in config from this by the current situation. So great, the controller pushes that config, and it keeps on pushing that config. It will pull the status from those jobs. Jobs don't push status, the controller pulls status. Keeps pulling them. If the job's not there, well, you know, the controller's going to go, oh, the job's not there. What this means is you just run this in a loop over and over again. Most of our code looks a bit like this. Given a nail and a hammer, hitting the nail until the nail looks like it needs to look like it. This look like it's in the wood, you know. Keep going at it. So what this means is if the source of truth changes in any way, so we get a new source of truth, that's good, and they've added something new, the controller can go, what the hell is going on here? That's not what I think the world looks like. I better add a new job to go along with that, and off it goes. And that's the loop that we're always in. Similarly, if that goes away, the controller goes, oh God, remove that job, make it go away. It's always going to hit the world until it's in the right shape. And we'll see how this impacts our ability to support the customers in production and gives us the ability to do some neat things of orchestration in the next few slides. Now this is just a pattern. It's quite a good pattern. I actually can't, and it's everywhere in the entire code base. It's everywhere. It's hierarchies actually. You know, you've got a job can be a controller itself, which creates more jobs and pushes information to those jobs. And it's been given its absolute source of truth from the parent controller, and it goes, great, that's the source of truth. I'm going to generate more config, generate more jobs, and make them happen. Well, this is just one-way data flow, and it's basically Elm architecture. I mean, if you've ever used React.js at all, well, exactly. Same kind of thing. You've got a model, the model is immutable, and you're generating UI from that model. That UI is a job in a way. You are transforming data and making something happen. Given that source of truth, you are able to rebuild the UI, and that's very important. So, actually, our server-side architecture looks just like our client-side architecture. I actually love to use the word architecture because it's just like really simple one-way data flow and code. You know, it's nothing special. So yeah, indeed, Elm architecture. I do implore you to go and check out Elm, by the way. That's the last time I'm going to mention of it. I'm not like going to like sit here and preach about Elm, but it does. So all of this is all fine and dandy, but only works so long as everything works. And in reality, we are software developers and we're pretty bad at our jobs, and things don't work. The ops guys, or the people that own the hardware and run things on, because they often do things on premise, they mess things up too, all the time in fact. So yes, absolutely, the next category is our approach to failure. How do we deal with it? So in reality, we have nest failure, we have bugs in our code, we have lots of bugs in our code. I mean, things seem to work absolutely great all the time until they don't. Disk failure, we get disk failure all the time. We're doing quite a lot of work on SSDs, writing all the time, because we're doing a lot of video and audio, and SSDs occasionally just go pop. Boom, that disk is now dead. That node is now completely useless to anybody. That's a problem. And of course, human error. That's the most likely one, really. It's nearly always human error. Someone's always typed in a bit of config that makes absolutely no sense somewhere and pushed it via an API, and just falling over and go, oh, that's awful, what's going to happen? So inside an Erlang application, this is actually an automatic thing. You have, using the controller and job terminology again, a controller is just a supervisor, and a job is just a gen server living within that supervisor. Again, I appreciate you don't really know Erlang. That's cool. I think that's good. If that job goes away and crashes, the gen server will go, it's crashed, and create a new one. And that's how it works. It's just built into Erlang. You accept that things will occasionally crash. everything you build in Erlang tends to look a little bit like this. There we go, there's a supervisor. So this is a supervisor that has some children, some transcoding going on, there's a bit of commentary going on depending on what the contribution is in your web. We might start a different child. We don't need to write any code other than telling the Genser, the supervisor, what to do with these jobs. So in this case, one for all. If one of these dies, the whole thing is all the other jobs get killed as well, and we'll do max 10 restarts within a certain threshold. Great stuff. That's a very simple supervisor. In reality, in applications, you tend to have layers of supervisors and layers of children, and Erlang just takes care of all that for you, which is super nice. I think most systems should be written like this. Between Erlang applications, you can do distributed Erlang and play around with remote supervisors and things. We don't tend to. So you've got a controller and you've got a job, and that's happy days. The controller can request the status from the job, as mentioned earlier. And one of the things in the status will be the kid of that job somewhere in the system. This Erlang setup we've got going on means all of the remote processes can be spoken to by any other remote process. They just can. They all sit within EPMD and can chatter away. Obviously they don't, but they can. So we get that, and the controller can do what's known as a monitoring operation on that job. So you go, Erlang monitor, this PID, please. And what that means is the controller gets a notification if the job crashes or goes away. And it's not instant, it's all based on this net tick time value down here. On our actual hardware, when we're on premises and we've got these 500 node clusters, we can set that to 1 second and everything's absolutely fine and great. So within 1 second of that job, going, I'm now sad, you instantly go, panic, make a new job. Not a problem at all, let's get this on. Quite on these shortly. In Amazon Web Services, when we're doing things up in that area, net tick time can't be one. There's latency involved, there's things running in Asia, things running in America, and there's a bit more time involved there. So it's always at 10 seconds or so there. But that's not a big problem. Our customers are generally used to running everything on hardware. They buy these massive, expensive encoders that do one job. You plug something in here, plug something in here, input, output. And when one of those dies, your approach to fixing it is to go and order a new one, or to fail over somewhere else. A bug fix for one of these is waiting 7 months for the latest encoder and buying that well. You don't get patches, you just buy new hardware. It's very expensive, so if it takes 10 seconds for us to reallocate a job somewhere in the cloud, that's not a big deal. To them, that's still like black magic, which is good. It's just brilliant. We look really good all the time because the customers have really low expectations. I really appreciate that sometimes. You know, our job's quite easy because they have such low expectations because of the world they live in. Now, zombies are a really, really big problem. If you have net splits and disk failures and such like that, or you think you have one or whatever. A very classic example is you've got a net split here and the controller can't talk to the job, but as mentioned, the job is autonomous. The job sits there going, I'm doing my thing. Even though I can't talk to the controller, no big deal. But the problem is the controller gets told the source of truth is that there is no job. But you can't tell the job that. The job's just going and pushing data somewhere, it's doing its work. But the controller ties itself up anyway, because well, the job's not there, whatever, I'll just tie that away. And this split goes away and the job's still there, just ticking away, happily doing its stuff. Happy days. This happens, well, it's not anymore, but it can happen really easily if you don't write your code properly, which we don't sometimes, because again, we're developers and therefore highly fallible. So what happens here is that the job's always actually going, should I be alive? Should I be alive? What is it to be alive? Should I be alive? The controller goes, no, you shouldn't be alive. God, the hell are you talking about? Who are you? What's going on? And the job goes, seppuku, and kills itself. Everything has timeouts in the system. When you have state and you're pushing things one way, that works really well until there's failure. And actually what you need to do, any kind of state, is make that state transient by the introduction of keep lives, for the most part. This is reasonable. I think there's like 10 lines of code that every single job has embedded in it by a library, and the library just knows that the controller's there, knows to talk to the controller. If the controller's not there, it doesn't kill itself, because the controller might be restarted, someone might be tinkering with it. Normally me, I've normally taken it down for maintenance. The job carries on running. The controller comes up, the job goes to the controller, should I be there? The controller goes, yes you should. The job goes, cool. Job, or if the controller goes up again, job goes, oh no, it kills itself. Very nice. So keep alive with everything. This is actually valid even inside single code bases, single processors as well. For example, when we start a channel in one of our systems, it has to spin up quite a lot of secondary and tertiary jobs just to make the channel happen. For example, you might want to spin a package job to push that Akamai, and that needs to go on this node over here because that's the one of external network access. You might want to spin up a packager for pushing to some internal contributions, and that's fine. So you have a channel starting up and it goes, cool, create package jobs there, there, and there. That's good, those jobs are now doing their thing. You delete the channel and something goes wrong by deleting the channel, because again, we're programmers and absolutely bad at an awful lot of jobs. Channel crashes, packaging jobs are still just doing their thing. So the channel, if it has a packaging job, for example, has to keep saying, you're still alive, please give me a packaging job, please give me a packaging job. Now this is, again, hitting things with a hammer until they're the right shape. This is something that we have going on here. This is really useful because your approach to failure is the same approach to changing state. You know, they're the same thing, effectively. Adding new state or removing state from the absolute source of truth is exactly the same thing as that thing failed and I need to do one of them. They're all the same to us. It's just the system does not look like it should, make it look like it should. Good. So, our approach to development. When I first joined this company, I was like, how do I run projects? And they went, well, you get an Amazon key and that will start encoders up when you run locally. And make sure you go into console and close those encoders because they might be left behind when you possibly terminate stuff. And I'm just going, this is a remote working job and I like to work in coffee shops. And I don't want to be having to be connected to an internet connections to my job. This is absolutely nuts. So I went about modifying the project to make it all completely local on the machine. So we emulate absolutely everything these days. So there's a pop over here to make Erlang now to close that and see how to do this bit of work. They are run.sh. We love run.sh. Just spin that up. There you go. So we've got a fake Akamai, got a little SD subject going on. Each of these is a little fake CPU, little node in a little cluster, which is nice. Little hash coming up here. SD was right there. Yeah, there we go. This is good. Right. So we have the controller running over here. It's been set up. We have detecting all the nodes coming up. Over here we have 4 nodes availability in the system. They just have to waiting for jobs to keep getting to them. In that case, that's now not a job because we've always been on one encoder waiting to be allocated straight up in the system that we have here. We have all the spare mounts over here, so we have failover. So if a controller goes down, another one takes its place. Which is called planning grade. And this is all completely local, which is quite nice. If I actually go into a thing over here, you'll see I'm just a Docker for this. I don't really care what we use here. This is the only place we use Docker in any of our systems. We actually hate it for production purposes, but because we do a lot of like really cool hardware stuff. But each of these has a known IP. They're on the same little isolated network, and they are effectively capacity within a cluster for us to allocate things to. And every system that we build now does this. So anyone can upload one of the Git repos, build it, normally build a metric ton of native dependencies, because to do encoding jobs you need to have quite a lot of really cool crap there. But everything is buildable and runnable by run.sh, which is good, because it means my boss, when he occasionally opens one of my projects, can actually go and fix things in his code when he's broken my stuff. Because he does that sometimes. One of our guys is a mad, cool engineer and works on all our encoder stuff. He gets very excited sometimes and writes a lot of code, and the code doesn't always work. And rather than trying to fix it in isolation, you might just spin it all in the context of one of our projects, because it's easy to do that, and find the bug that way, because it's often very context dependent. Obviously, once you understand the context, you can do that isolated as well. But having this ability is really important. So my instructions to him when he popped back were to this project. Steve, there we go. Let's create one of these files, please. Yes, this thing. What's he currently watching? BBC World 1080i and Stargate. That's good, yes. He went through a phase of using Strictly Come Dancing as his video source of all the systems. And I got really fed up with that one episode of Strictly Come Dancing. When I watch Strictly Come Dancing, it's an absolutely abhorrent show. I mean, it's just so happy and colourful. I'm not into that at all. Absolutely not. Look at the example of debatable look. There you go, exactly. So that's what we're emulating in this case. This is a Contron. It's a company that builds these little 2U units, or 3U, just 2 I think, just 2, yeah, that hardware-wise is also failoverable. So 2 power supplies isolated, you pull one of these out, it carries on working. The fans at the back, you pull them out, it carries on working. It just makes the fans work harder. You can just pull these out while the whole system's working, the CPUs themselves, and that CPU just stops working and everything else carries on working. It comes in again, it turns up again, things aggregate to it. It's a really cool piece of hardware. Some really cool demos of our failover abilities at an expo in Amsterdam last year, where you just talk to the customer and say, yeah, the channel was running on this one here. You see the IP address just there. That's good. And as you talk to them, so they know to pull it out. And the video carries on playing, you see the IP address change, and it carries on working. And they're just looking at you holding this CPU in the hand. And you go, look, what's the CPU? Touch it. It's really hot, of course, because we sat there encoding for the last hour. Probably should have done it, actually. Killed 2 of their nodes because of static. And like £5,000 each. But fine, it wasn't our hardware, it was theirs, so. Intel asked us to go in their stand and demo their hardware, so we demoed it, and unfortunately, you know, while you can pull things out and do hot swapping, you shouldn't do it every 10 minutes. It's not good. But it's the kind of daft things we do, you know? So yeah, we should. So yeah, we mirror our production environments locally is what I'm basically saying. So it means you get fewer supplies when you actually go and deploy. Obviously we do have development environments we deploy to which are a lot more realistic. So it's quite nice actually, our customers buy this hardware and leave it in one of their facilities and say, that's your dev environment. And you go, that's great, I've got an 18 node cluster just to play with. And each one of these has a GPU on it, so I can top mine with Bitcoin. I don't, obviously. That's being called, isn't it? Yeah. There's no Bitcoin mining in our software, I promise you. Yeah, so you get faster iteration by doing this, which is nice. Obviously, the jobs themselves, they are runnable in isolation as well. So you haven't got spinning up a whole system just to make new features for a packager, for an encoder, for a commentary job, for it. Is arduous. You don't spin up this massive thing, not least of all because, again, I like to work from coffee shops. I'm on battery, and spinning up a fake cluster of 2 encoders, 3 channels, and 3 encodes going on to feed that with information makes my battery life, I think, go down by 60, 70 to 8%, like that. Cool stuff, but not practical when I'm working in coffee shops or pubs. Mostly pubs these days, actually, I'm entirely honest. My job's very stressful. So our approach to testing, I covered this a little bit before, but let's talk about it. So unit testing, we do it once code's lived for a little bit. Because as mentioned, we often change our minds and delete code willy-nilly. So a lot of upfront effort really isn't that applicable to our use case. But we do have extensive unit tests for any core technology. So our orchestration, our auctioning, our scheduling, everything about that has comprehensive sets of unit tests that you can just run and actually test that it's meant to do what it's doing. Because this is now understood behaviour, this is stuff that we've written a few times, and we've gotten to the point where its job is well understood because it's being shipped in 3 products, and we go, great, let's actually make that a real library and add things to it. Very often, by the time we get to the 2nd or 3rd iteration, we go, cool, we haven't got to do that anymore because something else happened. So you just delete that library entirely and forget about it. Integration testing, let's just meh, really. Don't really care about testing these things in smaller units, bigger units, and together and whatever. Cache contributions is much more interesting. So, with all of our systems, there's a lot of capacity for things going wrong. And you want to run everything in your system in a real environment and just start poking at it to see what happens. I think, as I'll talk about this next, I'm not going to go into massive detail about it. But here's one of our chaos monkeys, just one of them. So if I call this little function stress worker, it'll sit there in a loop, and every 30 seconds it'll do something. It might just SSH into a node and init it. It might go and kill the bootstrap running on that node. It might just delete the absolute truth, so the channel sessions, whatever. It might make some events. It might do any of these things, and it'll just sit there doing that. Now, if there's a problem in the system, this brings it up. Normally it's a performance problem because I've been an idiot and I'm writing the database far too much. We're using etcd in this particular system to support our clustering. And the problem with using consensus-based systems like etcd is any write you do gets multiplied across the cluster. And I think I was doing constant writes of about 100k a second and never stopping. And Etsy didn't have a chance to keep up with that. And at one point was writing, I think it was 400 megabytes a second per disk, which obviously you can't really do very easily. So the whole thing died. And it was my fault. This brought it up. I was like watching amazement as the entire cluster just died. It's like, oh, what have I done here? Guys, could you go in and turn it off on again, please? Because I actually can't SSH into it anymore. So we're ruthless about this. I always say to the customer, if you want us to go into production with this software, we have to run this over the weekend. Because this is TV we're talking about. You can't have a TV channel go offline for a couple of days just because no one's around to turn it off on again. So we have to trust it. Releasing to production is running a single script. We can do it whenever we want to, we just choose not to because we want to trust the system before we do it. We can't run this in production because, as mentioned, it's TV, we're talking about a lot of cases, you don't think turning off, even periodically. Their downstream devices are very sensitive. I'll give you an idea of that. We have things going into this probe which normalizes video audio and goes somewhere else, and we're sending 15 megabits a second video to it. It needs 15 megabits a second, and it needs it accurate within, I think it's 25 milliseconds, so every 25, divide that by how many, 100 milliseconds, 40, so divide it by 40, it needs to be exact. It needs to be a mill pond. And now obviously hardware, it's really easy to do that because they just do a little loop, push data out and it just works. In software, where you haven't got the real-time capacity for doing that, it's quite a complicated thing. So, long and short of it is, we're able to do that, which is great, but if we dick with our system and modify that anyway, everything downstream dies because this entire ecosystem is dreadful. Nothing likes anything that does not look good. Our stuff doesn't care, you can get any old crap and we'll do our best to keep going. But we're software, everything else is hardware. So, generally we do releases to prod if the Chaos Monkey runs all weekend and there are no zombies, no crashes, no failed jobs. And when I stop the Chaos Monkey running, everything that was broken stops being broken. And if that doesn't happen, I know there's an issue. Of course, very logs across the entire system, I can go and see what the issue was and go and fix it. But it doesn't really happen anymore. I joked earlier about the days since support issue in production, but I actually do keep one at my home, which is days since the last zombie was seen. Because every now and then I assume, whenever there's a problem in the system, oh, it's probably a zombie. It never is a zombie. It never is. But I assume it is. Apart from last week, so it's been 7 days now, and it was a zombie, and I went, it's probably not a zombie because I haven't seen one in a while. So there you go. I'm a bad software developer, this is why we do all this stuff. Exactly. So detailed testing of core assets is, it's a must, you have to do it. Full end-to-end testing of the entire system is absolutely a must. Most things in between those two at the spectrum don't really add that much value for our use case. We keep saying that over and over again, but it's implied. The way we do things works very well for us. Don't go and take anything I'm thinking about road. New code is likely wrong, and it's going to get to this anyway. It probably does the wrong thing, it probably misunderstood the requirements. And by we've misunderstood the requirements, what I actually mean is the customers misunderstood their own requirements and given us the wrong requirements, and we've misunderstood them even further. So it's probably 2 different degrees of wrong. So we'll get there in the end, but it's probably wrong to begin with. Monitoring, well, this is good. These are big systems, we're doing hundreds of thousands of events a year. Of course they're big systems, relatively. So in a standard production facility, we'll have hundreds of CPUs sat there available for capacity. There's thousands of moving parts, lots of things will go wrong, and we have to surface the problems. A standard example of this can go wrong is they give us bad video input. There's a very good example there. They always give us bad video input. For example, audio and video might arrive 5 seconds apart as they hit our encoder, and we're a low latency system. But if you have video and audio 5 seconds apart, you have to introduce 5 seconds of latency to put them together again. Because everything downstream of us will fall over if we don't give it exact amounts of video and audio. So we've got to surface all these problems from somewhere in the system. These are done. So the Darwin children and things like that, InfluxDB, Readman, Refine, or whatever. And we've built great dashboards. That's not one of our dashboards. We've built amazing dashboards, and they're really good sales tools. If you go into a customer and show them amazing graphs and dashboards, they get very excited. They go, we can build those too. Yeah, you can. Data's all there. They don't actually. In reality, you install it, you run it. They look at it, it goes very shiny. and they never look at it ever again because they've got more interesting things to do than look at dashboards that don't mean anything. They just don't. This is great for selling stuff on a stand. It's not actually good in production. So yeah, they're really good demos. But they're bounty metrics. That's what they are most of the time. You don't need them. That's not to say we don't support them. We still have the capacity for them, and we always spin them up against our system because, as mentioned, they are sales tools, and we are trying to make money. So we do go through this. We go, look at these great dashboards, knowing full well they're never going to use them. But that's fine. We haven't put a lot of energy into supporting them, so it's okay. No, actually, in reality, what you need is something more business-centric. So every node can post this localhost /flags if they need to. Every node running Nginx, which knows how to redirect to any other node because they can do DNS to any node in the system, and it will know how to redirect them to the right where they're going. That means every node can actually find control, which means every node can send things to control. So control just got in-memory set flags, that's it. In this case here, I'm job ID, action 1337, and I've got this continuity on this source. Help! And the manager sits there looking after this stuff, in memory, has timeouts and all this information, keeps a counter, and if the counter goes above a certain threshold, it goes from orange to red. So, you know, there it appears on the channel and goes, there's no traffic on the source, oh, this is dreadful. Or even better, you build a very business-centered dashboard here. These are all jobs in the system. Grey means it's not allocated, green means it's great, fine, orange means uh-oh. Something bad's happened there, and you can get from there to see what the issue is and see what happened, and again, they haven't got to ask us what's going on, because they can see it. This is a lot more useful than shiny graphs and dashboards. You put this on a big monitor in the big room, and they go, what's that orange bit? Go do that. Most of the time, these are all green. We don't have flags for silly things. The problem is, if they were orange all the time, then people would ignore them. So they only go when they're important, which is good. We also have really good introspection into our system. This is a very small workflow for doing media. I think what's the one currently doing? Yeah, so we've got an audio decoder just up there, pulling things in from this bus here. It's metering the video flash. It's syncing the video and audio and sending it out on a bus over here so we can do some streaming. Over here we're doing some code work, we're generating some silence and merging that with some commentary. We're doing a resampling of the video, of the audio here, and turning it into 48,000 kilohertz, 48 kilohertz and whatever it is. And then we're syncing that together with the silence. And it's all there. Every single one of those has detailed information about how many frames it's seen, and also will raise flags and turn orange and yellow if they're bad. This is for us, not for them. We support ourselves. So we had problems because everything else is just noise, basically, is what I'm saying there. Our approach to disaster. Well, things still go wrong. So we built this great system, we ran Chaos Monkey, everything seems absolutely fine, and then for some reason on a Friday, a package doesn't get allocated when it needs to be allocated. And I got to say on Friday I'm in the pub, and I'm not answering support calls, so I don't want to answer, I don't want to do that. We got, or something crashed, the job's got a bad state, and it all comes down to state being wrong at the end of the day. Well, we don't want the callers, we don't want them to do that. It's not what we want. We employ a pattern called the fix it yourself pattern. So if the system's got an absolute source of truth and can regenerate all the jobs from that absolute source of truth, and most of the time those jobs are going to be correct unless the absolute source of truth is wrong, then if you give them buttons where they just turn things off themselves, kill a channel, kill a packager, kill a conversation, kill a whole node if you need to, we'll reallocate everything, it's absolutely fine. So our approach to fixing absolute disaster when things have really gone wrong is to give them buttons to delete state, because the system can react to that the same way it does to failure, and the same way it does to absolute source changes. It's the same code path. We get this for free, and more importantly, they don't give us a phone call, and that's good, because I'm actually scared of the phone anyway. I don't answer the phone. It's not. I'm not into that. I like emails, you know, or text messages. No one wants to text me going, "System's not working right. Can you look at it, please?" Because I'm not looking at that right. Like I'm in the pub drinking beer. So we can do this because the absolute source of truth probably isn't broken, nearly all the time, which is good. Our local state probably what's broken. So if you delete the local state and recreate it, then you just move on with your life. And again, in reality, it happens once every month or two. But that's, again, if you're keeping track of support calls in production, those are support calls that we didn't get because they just fixed the problem themselves. which is just like hallelujah, you know. I can talk about all the stuff like House Come Home, I really can. Apparently last night I was doing something like that in the bar, but apparently I was talking about Erlang. It sounds unlike me, I have to say, but apparently it's just not an Erlang talk, right? I mentioned it, but it's not Erlang talk. Erlang makes it easy, but I can't just go on about it. But I know I was right, look at that, see, it's 5-2. I was actually coming bang up on it. Got a moment for a few questions if you have any, if I just like thrown speech at you. Got any questions? None at all?
Do you have any monitoring alerting setup? I mean, like, do you guys get paged? I saw you built a dashboard or something like that. But like,
yes.
So like clustering down, do you get a page or something like that?
Yes.
Okay.
We would. We don't, but we would. Yeah, pretty much. In reality, I'm not on support. No one's on support. They'll probably call my boss, Adrian. I'll probably call him, and he'll go, oh, panic, and then he'll call me. And because he's calling me, I'll pick it up because I know who it is. And also, he probably knows the problem in, so he could get me if he needs to. So yeah, we support contracts have SLAs and we have to adhere to them, but again in reality we don't hit a support contract, you don't need to do the support. If there are problems we'll get them in depth before you can throw it away, at which point it's a live system, so it's absolutely fine to play with. I'm surprised no one asked me what about Kubernetes or Nomad or anything else. I had a slide prepared for you. I was QI style, but never mind. I was disappointed. I need to maybe drop some hints in during the talk to encourage this to happen. I will answer my own question at that point. When we started working on the stuff, these did not exist. This is new stuff. We don't go inside containers because our foray into containers 3 years ago did not go very well. It turns out that they were just an abstraction we didn't need. Erlang releases are self-contained, they're just tars, you just unzip them, done them. They don't need to be put in a container, they're entirely self-contained. But the most important thing about all these scheduling and orchestration systems that are out there is that they're all new for the most part, and they all don't do quite what we need them to do. In 10 years' time, once the field has stabilized a little bit, we'd probably delete all that code and start using something like this. But this is core business to us, how we actually handle failure and how we do the scheduling. And it's always done in a very business-centric manner. It's not generic jobs running, it's SLAs for different kinds of jobs and how we actually want to restart them and how they might impact other jobs if they do go down configuration-wise. And owning all that stuff makes a lot of sense to us because it's one of the biggest demo pieces, pulling things out of this Contron and everything still works. We need to own that stuff because it's core business. So that's the answer to that question asked. Yes?
What do you do with etcd? What do you use it for?
We use it as a config store, effectively. We also heavily leverage leases. We have a floating set of managers running, and only one of them can be active at any one time. So they take a lease out, or try to take a lease out, and the one that wins spins up all the end servers and becomes active. Every 23 plus random 60 minutes, hours plus 60 minutes, it will actually turn off. Control closes itself down, and as it does so, it'll run a defrag on the local node. So it'll turn itself off and run a defrag. One of the other controls will come back up again because it's got a lease on SD and carries on working because you've got a quorum. And that's what that's for. We do get node failures, they do die. So you need to have your data store distributed, and you need to have the ability to do failover internally with who's controlling information. Again, because SSDs do die. We're running these systems, we're doing a lot of encode work, we're using both the CPU and the embedded GPU on the QuickSync and make them very hot all the time. So no matter how much money you spend on these systems, they do wear out and they do fall. They're still cheaper than hardware encoders though, like by a long shot. Like we went to our clients and went, I'm not sure you've got capacity for the channels you want to in the Chrome production facility. And they went, oh, it's fine, we'll just go and buy another 32 node Moonshot server. It's like, we'll just go and spend £50,000, £100,000 on a new blade data center because that's still cheaper than buying hardware encoder. So we don't mind the failure because it's inherent, but it's still cheaper than buying into this hardware release upgrade cycle Doing things in software gives you the ability to react to things much faster. As mentioned, we react very fast. We fix problems when they arise immediately, and always impress our customers because they have such low expectations, as I said. Right, yes, that's us, time-wise. Thank you very much for coming in from the sunshine. I appreciate it a lot. Thank you.